Okay. First of all, I want to thank the organizer for the invitation here in this nice place. It's the first time for me in Galileo Galilei. Okay, the talk will be divided in two parts. The first part is about balance metric. These are type of Hermitian metric that appear in non-Kähler geometry. So all the time, the manifold that I will consider will be complex manifold, non-Kähler. And they have a nice relation with the Hull-Strominger system. We will see how. And the idea, essentially, I will present two papers. The first one is a joint paper with Grancharov and Verbitsky, and it's about a recent construction of balance metrics, starting from hyperkähler manifold. And the second part is still a joint work with Grancharov and also Vezzoni from Torino. And in the second part, we will see new solution, for non-Kähler solution for Hull-Strominger system. And the solution generalizes the Fuyao construction. Essentially, instead of considering K-free surface, we will consider K-free RB surfaces. That's the idea. So let's start. Let's start with balance. I will start with an overview about balance metric. Okay, definition. So let's take a complex manifold, a complex dimension n. Here I will identify the metric with the fundamental 1-1 form or Kähler form, omega. And the condition is essentially that if you take the wedge product n minus 1 times, that wedge product is closed. So we will have the condition essentially that omega is co-closed. And that condition makes sense for n bigger than equal than 3, because for n equal to 2, you will see that you have simply d omega 0, and so is the Kähler case. So we'll consider that case. Okay. Essentially, there is a first result about when a Hermitian metric is balanced. This is a result to Paul Goduchon, and it's related to the Laplacian associated to the differential D, the Laplacian associated to del and del bar. Essentially, if you have that relation, that's equivalent to the metric, to the Hermitian metric to be balanced. But I think the first, this type of metric appeared the first time in the paper by Greyer-Vella, but the first, let's say, place where the metric appear with nice property is the paper by Michelson. And essentially that condition to have, for a complex manifold, to have a balance metric, is in terms of current. So we use a duality between differential form with compact support. We work on that. And so it makes sense to talk about 1-1 degree and also about positive for the currents in terms of the form by duality. And the condition is essentially that you cannot have any positive currents at degree 1-1, which is component of the boundary. So it cannot exist a positive current T such that T is the del S plus the bar S. That's what happened. And that's nice. It's a nice condition. We will use this duality current later for construction of balance metric. But one thing that is nice, that you cannot take some obstruction. So in general, there are not many obstruction for the existence of such metric. And one obstruction was found by Michelson, and is essentially the condition, if you have a compact complex manifold, the condition is that every compact complex manifold of codimension 1 has to be homologous to 0. That's the only known, let's say, obstruction about the existence of such metric. And for instance, one can apply that obstruction to Calabi-Ekman manifold. So we have something like, let's say, the product of two odd-dimensional spheres. And then you have the holomorphic, the structure here is just essentially the natural projection that you have a CP, sorry, I forgot, of course, the product of the complex projective space. And if you take such complex structure that metric, holomorphic, then you cannot have. So for instance, it's still open. This is an open question. It's simple, but nobody knows. If you take the product of this, okay, with a complex structure which is not given by Calabi-Ekman structure, this doesn't know if it has a balance metric or not. We will see later by using transition conifold that is possible to prove, that was done by Li and Yao, that if you take the connected sum of such product with K bigger than or equal than 2, this we know that you have balance metric, but in this case, one doesn't know. So it's still an open question. Simple open question, but this difficult to prove. Okay, let's go on. What are the examples? Another nice construction that appear to be balanced is a twist space. So you work on the bundle of almost complex structure, which are compatible with the metric and also orientable. And the idea that the base, the four-dimensional Riemannian manifold, you have a condition on the curvature, on the wide connection. So it's anti-cell dual. And when you do not take S4 or CP2, you get something which is non-killer. That's by each result, let's say. But there is a nice way to go from killer to balance. Just take a B meromorphism. If you start with a killer manifold and you apply a B meromorphism, then you get something which is balanced. That is U by Alessandrini and Bassanelli. That was shown by currents, using the currents. And so in particular, we have two classes, a non-killer and balanced manifold, let's say. These are the Moyet-Jean manifold that are obtained by B meromorphism, starting from a compact projective manifold, and more general Fujiki class. You just start from compact killer manifold, and you apply the B meromorphism. But there are very simple construction. Is just take a complex group, unimodular. We want that you have a compact coefficient by lattice. And so the complex structure is the bi-invariant one. Any metric compatible that bi-invariant complex structure give you a balance metric. I will go back to this construction later. And as I say, there is this nice construction by Li, Fu, and Yao. And here you saw with Calabi-Yao free-fall. So in the killer case, Calabi-Yao. So with Keller-Ricci flat metric, and you apply what is called the conifold transition. So roughly speaking, you take a contraction by rational curves, so copy of CP1, with a normal bundle of type O minus 1 plus O minus 1. You get something singular, and then you do a smoothing. And that's, for instance, you can apply in a nice way to get this example of balance non-killer. And there is a recent construction by Ducy and Podesta where they construct also something on simply groups on non-compact type. That is more or less dual to the real compact semi-simple. We will see in a moment. And that's conditioned to be on inner type, is just a condition related to symmetric space. So you describe the Lie algebra of your group in terms of symmetric space, but I don't want to talk about that. Okay. The first question, okay, one of the ingredients of the Hull-Strominger system will be not enough to have a compact complex manifold, already dimension 6 with a balance metric, but we want also that the canonical bundle is holomorphically trivial. So we want a section, a non-zero holomorphic free zero form. And one can look what happened in the homogeneous case. So here I mean that you take a complex structure which is invariant under the transitive action of a Lie group, and also you have a volume form that is invariant. If you look at that case, so these are, they have a nice description, geometric description, because these are principal homogeneous complex torus bundle of a product of what? Or generalized flag manifold and a complex parallelizable manifold. If you impose the existence of a balance metric, you can show that C1 is non-zero. So that's not the nice class to look at. We show that with Grancher and Bezzoni. But so in particular, you can see that the compact semi-simple Lie groups, if you take the Samuelson complex structure, so you just choose a system of positive roots that give you a complex structure, you cannot have such structure. On compact semi-simple real Lie group of even dimension. So you just choose a Cartan subalgebra, and you use, this is a Samuelson construction. Every compact semi-simple Lie group, real Lie group, as a natural complex structure. So you have something, you can work essentially in the abelian case, you choose something in abelian case, and then you play with the fact that you choose positive roots. And then with that case, you don't have any balance metric compatible with that. But you have, for instance, other nice metric that I will look later, like what are called pluriclosed metric. This is they have the structure generalized scalar. Generalized scalar structure is related to other metric. Okay, but on Lie groups, you have a nice way to have balance. In the nilpotent case, we have also classification, and in the solvable case, we follow Murphy-free-zero form, and also in this other solvable case. That's the almost abelian case, so you have a abelian ideal, a codimension 1, and also in the almost, so in some sense, the non-semi-simple give a lot of examples of balance. So it's really transversal to that condition. I will go back to this to understand better geometrically why. Okay, but let's see the construction. This is the construction that we had found recently with Grancharov and Verbitsky. I will present in a simple way, but can be generalized a little bit more. So the idea comes from a construction, a previous construction by Quinn and Wang. They describe some 6-dimensional compact manifold, which are on the same time diffeomorphic to, let's say, complex Calabi-Yau. What I mean with complex Calabi-Yau, I just mean complex manifold, and the canonical bundle is holomorphically trivial, okay? But on the other hand, they were also diffeomorphic to symplectic Calabi-Yau. So that means that the C1, the first chain class, associated to the almost complex structure, okay, compatible with the symplectic structure is 0, is vanished. Okay, so the question that we studied was, okay, can they have some special Hermitian geometry there, because it is shown that they cannot be killer. And related to the previous talk, they show on the other hand that these manifolds are formal in the sense of Sullivan. So the minimal model is formal. Okay, so I will review a bit how it came the construction, how it came out to generalize that construction. We show that, in fact, they have a balance metric. Okay, so how it comes the construction? We consider the Kummer surface. Okay, so that's a smooth compact surface that you obtain blowing up. What? You just take the T2, the complex 2 torus, and you take just the involution induced by essentially the multiplication by -1, and then you blow up the 16 double points. Okay, but you can describe also in other ways, it's exactly equivalent. So you take the surface obtained by blow up the complex 2 torus in any point and the evolution induced by that. That's the same thing. Okay, so what we can say about the fixed set of tau, this is a union, right, or the sectional divisor corresponding to the singular point, but that's the nice thing, that if you take the standard 2, 0 form, this zeta 1, wedge this zeta 2, and you take the pullback, this induces a holomorphic 2, 0 form on common. Okay, now we want to do something else. We want to apply, we will apply in a moment a way to, we will use what is now like a suspension or mapping torus. So essentially, you start with a manifold in general. You take the interval 0, 1, and suppose you have a diffeomorphism or your manifold, and then you identify P0 with Rp1. Okay, so you have a natural. Here we modify a little bit because we start with 4, and then we add the 2-dimensional, but we will use a different, we will use a product, the product with S1. So it will be like a mapping torus type S1. But let's see how we do that. So let's take a matrix with elements which are the Gaussian integer, and then we have that condition. That condition is the condition we will see later, that is a hyperbolicity condition on the cohomology of type 1, 1, and that ensures in some sense that the manifold that you construct at the end will be non-killer. Diagonalizable with eigenvalues. Of course, the eigenvalues is lambda and the inverse of lambda, and let's take the associated eigenvector, okay, on the induced cohomology. Good. What we have about the holomorphic 2, 0 form? The map preserved. Okay, the D1 wedge dV2, and if you denote, okay, the sum of the sectional divisor, we have a holomorphic transformation on the Kummer, so preserve the complex structure, that's good, and preserve the holomorphic 2, 0 form, right, by construction. So now we can take just the action. Another way to describe this mapping torus is just to take the product M times R and to take the quotient of the cyclic group generated by the diffeomorphism is equivalent, okay? So here we take the zeta action on that, so we take T2 times R times S1, and now we understand what I was saying before, because you see, you just act on X, but you don't act on Y. So at the end, you get something which is a mapping torus times S1, and the question is exactly the construction of Q1, sorry, mentioned before, and you get trivial canonical bundle by construction. You have a non-zero holomorphic 3, 0 form. Good. Okay, so let's look if that construction belongs to a general picture. So let's start with Koppa-Keller manifold, and let's take an automorphic, we preserve the complex structure. So it's only holomorphic automorphism, and we'll say that it's hyperbolic if the action on the real cohomology of type 1, 1 has a unique eigenvector with eigenvalue bigger than 1. That's you can distinguish the automorphism in terms of the action on the real cohomology, and using that and the lattice generated in C, generated by C1 and C2, we can construct in general what this is. The previous case is just a special case of this case, and you can see. So we just act, you see, on with C1, and essentially in the other we don't do anything, and we get something which is diffeomorphic to the product, the mapping torus of F times S1. Good. Okay, we want to something balanced. If we start with, now we add an extra geometric structure, not only Keller, but we also suppose that we have a holomorphically symplectic structure. So we have a hyperkeller structure is another way to define hyperkeller. And if we have a hyperbolic automorphism, we preserve the holomorphism in pletiform. Here, this condition can be generalized a bit because essentially what we need is just we need that it's preserving a volume, the manifold. And one can construct the holomorphism in plating, suspension, okay? And we show with Grantor-Verbitsky that in fact always you have a balance metric. This construction can be generalized a bit. You just need the two diffeomorphisms, which are holomorphic and commute and preserve the volume. And then it works on the same time. So we know that the previous construction has a balance metric, but you can construct more. For instance, you can generalize this not only with K3, but also with the Hilbert scheme of point of K3. You can apply the same trick. Is exactly the same, but I don't want to speak about that. I don't want to be technical in the proof, but the construction is using essentially by contradiction. So you use essentially the currents, and what you use is because when you do the mapping torus, let's say what is called MF, you have always a projection over S1, okay? So since we are taking something like the product times S1 cross S1, we have a projection, a natural projection on T2, on the two torus. So it's in particular a projection of a complex curve. And we can show, using Michelson result, that projection is in fact with the fiber, of course, M, you have here the hyperkähler, is essential in the sense of Michelson. What does it mean? It means that if you pull back the volume here, you do the pullback, this is cannot be aptly trivial. So it cannot be del of 104 plus on the other way around. Yes, del of something plus the bar. The applied homology cannot be trivial. So that's the way one can apply. One can do a similar thing for the real four torus. It's essentially similar. You just use the same metrics as before. You again get something which is balanced, non-Kähler. And in this case, you get a compact quotient of special type of solvable group by a lattice. So the nice thing here for the torus that you have everything explicit. You can find the metric. But one thing that we didn't find yet, and we would like to find a way, because the theorem is an existing result using current. But how, since we want to study also solution for Hull-Strominger system for that case, because you have a rich class of example, we need to find also an explicit metric. We have no idea now how to find an explicit metric. So it's an existing result, but not, the metric is not explicit for that case. Good. Before to go to the Hull-Strominger system part, I want to mention that in fact, okay, you can have now in literature, there are many types of, let's say, non-Kähler Hermitian metric, and they play a role also in relation to theoretical physics. And one type of metric that is quite now understood, and that's a relation with generalized scalar geometry, so generalized geometry, is a notion of pluriclose. So one can ask, okay, let's start with omega, and let's ask on the same time, for the same omega, the condition, of course, n bigger than equal than 3, the condition to be co-close, that's a balance condition, plus, on the same time, what is also called strong Kähler with torsion, so the pluriclose condition. So omega is Didybor close. Okay, what happened? Here the proof is given in different way, independently by Alexander Ivanov and Popovici. Essentially, if you impose on the same time the same condition, the both condition, you get Kähler, you go back. omega is scalar. Okay, with Vezzoni, we conjecture, it's still open, this conjecture, because every time you have a balance metric, and you don't have pluricross metric. And every time you have balance, on the other hand, you don't have the other, and it's not clear why. Of course, you want an example, a compact example, which is non-killer. And in the non-compact case, in fact, there are examples, solvable Lie groups give examples. So the conjecture, which is still open, is okay, let's start with a compact complex manifold admitting a balance and a pluricross metric. So two different metrics compatible with the same complex structure is scalar. That's open, and is in fact no, all the example, and also that was a bit more complicated using the currents, the previous construction, the previous manifold obtained by hyperbolic suspension. We show using currents that was more complicated. They show that it's balanced, in fact, that they are not pluricross at all. So again, you have some, and you can see also for compact semi-simple Lie group. You remember they are no balance, but on the other hand, it's very easy to construct pluricross. You just take a bi-invariant metric compatible with the complex structure, with the bi-invariant complex structure, and then give a pluricross metric. On the other hand, you can, this is just now, you can ask something different, and you can ask what is called a steno-killer. And that corresponds to the case dd bar omega n minus 2, 0, okay? So of course, for n equal to 3, it's just pluricross. It's the pluricross case. Okay, again, if you impose that condition, this one, plus balance, you get killer. But that was a question posed by Zegledi, Tosatti, and Vainkov that was related to some flow, some Hermitian flow, in relation to some complex Monge-Ampère equation. And there was a similar question. So you have a compact complex manifold, and you ask if you can have two different metrics, one which is balance, and the other one which is a steno-killer. And we show, of course, this is in dimension bigger than 3, so it is bigger than 3, that this is possible. So in some sense, the pluricross condition is much stronger, let's say, than the other. And then here, the construction come out from some homogeneous space. So you just take SU5 over T2. Let's give an example for that. So it's quite curious. It's still open, so I don't know. Okay, I am still working on that about showing, and maybe it's an approach, but I don't want to talk about this here, is using some geometric flow. We have geometric flow evolving the pluricross condition, a geometric flow evolving the balance condition. So a possible approach maybe is using that. Okay, let's go to the Hull-Strominger system. And I will show the construction, solution that we found. Okay, I am not the right person to talk much about that, but I just want to give a motivation what is coming. So that's describe the geometry of compactification of heterotic superstring with torsion to 4 dimensions. So we have a link from 10 dimension to 4 dimension, and locally the manifold will be a product of a 6-dimensional manifold from locally Minkowski space, and the object will be not only this 6-dimensional manifold, we will have some geometry there, we'll see which type of geometry, but also we will have a gauge vector bundle E. That's also has an important role. And so the idea is to reduce all the equations required by superstring theory. Here I say all the equations, but we'll see that one part of the motion equation is missing, in fact, in the discretion. You need an extra condition for that. To the 6 manifold here and the gauge bundle there. Okay. Motivation for that, the first solution for the first important solution for that system were found by Gandelas, Horowitz, Strominger, and Witte in 85. And okay, the type of structure that you have here is in fact what is called an SU-free structure. Okay, so we have a free zero, we have a complex structure, we have a free zero form, and also a 1-1 form, a metric, omega. And the flux up to a factor is essentially something like d minus d bar omega. That's the idea, up to a factor. So that's the flux, that the free form. And the flux-free case, so when the flux is zero, essentially to have a flux zero, it means that here you have a product metric. We'll see in a moment what happens if you have not a product metric, but a warping metric. So in that case, one can construct a solution just taking as E, the tangent bundle of M6. And what appears here, that this SU-free structure has to be a Calabi-Yau structure, so a Keller-Ricci flat metric in particular, and the fact that you have such solution comes from Yau theorem for solving the Calabi conjecture. The case where we are interested is the case, the non-Keller case. So in that case, we will not have anymore the product metric, we will have the warped product metric. So that flux will be non-zero in that case, and the structure force still M6, the 6 manifold, to be not anymore Calabi-Yau Keller, but Calabi-Yau non-Keller. So the canonical bundle is still holomorphically trivial. Okay, let's see the equation. The equation are the following. So we have a compact complex manifold, complex dimension free, and we have a nowhere vanish holomorphic free zero form. That makes the canonical bundle holomorphically trivial. And let's take a complex vector bundle over M, and we denote by big H, and Hermitian metric along is 5. And then we have this constant, alpha prime. From physics point of view, alpha prime has to be bigger than or equal than 0, but mathematically, we'll see later, is also considered the case alpha prime negative. The Hull-Strominger system is the following. So the first equation is, okay, here FH, I just denote the curvature of the chain connection, and I think as a 1-1 form with value in endomorphism. So it makes sense to compute the trace and whatever. So the condition, that condition corresponds to the fact that the holomorphic bundle E, if reducible, is what is called polystable, stable using the slope, essentially. And the second condition is essentially if you multiply omega wedge omega by the norm of the free zero form with respect to small omega, there are too many omega, sorry, too big omega and small omega, this is closed. So it means with conformal change, you get a metric, a balance metric. And the third condition, that's the more difficult to solve, and in some sense is a curvature condition. That's generally the Ricci flat condition. Because this condition involves the two curvatures. One is the curvature, FH, and the other, in principle, is a curvature of a metric connection, R nabla. Again, viewed as a two form with value in the endomorphism of the tangent bundle. Here you have a choice, in fact, of such nabla, because it's just a metric connection. We will choose a case that nabla is a chain connection, but there are also other constructions where you don't need, and in fact, this is not the right, we say the chain connection is not the right choice from physical point of view. We'll see in a moment. Okay. So what we can say about the Hull-Strominger, we can say that it's a generalization of Ricci flat metric on non-Keller. free fall, coupled with that Hermitian Yang-Mill equation. That's equivalent exactly, as I said, that to ask that the holomorphic bundle is stable. And we can see again that we have exactly that Calabi-Yau Kähler manifold are special solution. You just take E equal to the holomorphic tangent bundle, T10, and H equal to omega, and then you have everything. So that's nice. Okay, this is the link with the balance, as I mentioned. So we just ask with the conformal change, we get a balance metric. By Li and Yao, it was not written, originally it was not written in that way. It was Li and Yao that formulate the equation in different way. Oh, sorry. Okay, thank you for letting me know. Okay. Okay, so it was not Li and Yao that they formulate later? Okay, sorry. I didn't know. Yes, thank you for letting me know. Okay, and this is can be viewed as a notion of canonical metric because you have a condition involving, let's say, the curvature, right? Okay, the third equation is a more complicated equation. It's also called the anomaly cancellation equation and couple the two metrics. And that is exactly the more difficult equation to solve, essentially, because to solve the first two is, okay, the second maybe is less easy than the first is less easy than the second, but you can. But the third one is a more involved equation. Okay, what we can say about the choice of nabla? We have many choices. If you impose that the nabla is not only preserving the metric, but is also preserving the complex structure, you have a family, a one-parameter family by Goduchon result. And this includes the Chern connection and the bismuth connection, the Strominger maybe is called also Strominger connection. So the connection for which the torsion is a free form, is Q-symmetric in all the topic. From physical point of view, as I said before, one has that alpha prime is bigger than or equal to 0. And of course, alpha prime 0 corresponds exactly to the Kähler case because you have dd bar omega 0. That's exactly the Kähler case. The negative case, there are nice paper by Fong, Picard, and Zhang about that. And now we will consider the Chern connection. But here I want to point out from physical point of view that this is not enough to solve all the equation, to find what is called a supersymmetric classical solution. Because to have the full solution, one should have this extra condition. So nabla should be an instanton. So again, the 2-0 part, the 0-2 part of the curvature has to be 0. And if you do the wedge of your curvature to form wedge omega squared, this is also has to be 0. And the Chern connection doesn't satisfy that. But mathematically, it's quite nice because there is also some conjecture from the fact that if you have different solution of the Strominger, then you can go from one solution to the other applying conifold transition that I mentioned before. So it's nice to learn more, to have more solution, to understand also this other conjecture. Okay, here I just mentioned some non-known, non-Kähler solution, but there are more, okay? I mentioned, okay, the first one was constructed by Fu and Yao. This is constructing on a torus fibration over a K-free surface, and that's a construction that we generalize, changing the base. A joint PhD student, in fact, is working on further generalization. We'll see in which way to get more example. And then there are also construction coming from Lie groups One construction, the first one was shown by Marisa Fernandez, Stefano Ivano, Luis Ugarte, and Raquel Villacampa. And that was in a simple case like taking the Heisenberg, the Heisenberg manifold, Neal manifold of dimension 5 times S1. And Fei and Yao constructing also what I mentioned at the beginning, like complex parallelizable manifold. But they use, in that case, they use all the family of Goudouchon connections. So for all connection in the Goudouchon family, they construct solution. And Gancho found another way to describe the first example. But the nice thing, there is a lot, Mario Garcia Fernandez worked a lot about this Hull-Strominger system. And one nice thing, one nice construction is that he found out new solution on torus fibration over K-free surface using T-duality. T-dual solution. So the usual T-duality can be extended also in the balance case. Is slightly different, and he found out that you can find solution also in that way. And there is also a nice construction, again involving compact hyperkähler manifold. This extends a previous construction by Alfred Gray, essentially using fibration over a compact Riemann surface. You need genus G bigger than equal to 3 for the existence of balance metric, essentially. And we fiber a compact hyperkähler manifold. That's also nice. But let's go to the construction that we generalize. So I start to review how we get the construction, how we generalize, changing the basis, essentially from K-free surface to K-free orbit surface. And let's go to the construction by Goldstein and Prokoshin. That's generalized the Calabi-Ekman construction, in fact, because you start with a K-free surface with a Ricci flat Kähler metric, small omega s. I will denote by omega big S, the 2-0 form, the holomorphic 2-0 form. So every time you take a 2 anti-cell dual, 1-1 form, you just need, okay, there I forgot to put 1 over 2 pi. I should put that, but I forget about that. They define integer cohomology, then they associate in a natural way a toric fibration. And essentially what happened that you have this connection one form such that the differential of the connection one form, that's just Chen-Weil theory essentially, is the pullback of omega I. And so the complex structure is such that fibration is holomorphic, and you have in a natural way holomorphical trivial bundle, because you just take theta and 1-0 form, and then you wedge with the pullback of the 2-0 form, big omega S, that you have in the K-free surface. And then it's quite natural to have a balance metric, because you just say the pullback of the form down, and then you just use theta wedge, theta bar, essentially, the vertical part. And that's balance. So the way how you can find solution, that's what is called Fuyao on Sats. You just modify. So instead of, if you remember the previous expression of the metric, you modify the horizontal part, multiply, instead of considering the Kähler form on the K-free surface, you multiply by a scalar function, okay? So U is just a scalar function. And then you write down the condition for having, okay, to have a holomorphic stable bundle over a K-free surface is insurance essentially by Mukai theory. We will see in our case what we need. We cannot use Mukai theory in our case. We need something modified. But anyway, that's the condition that I write down, the complex motion pair equation that appear is exactly the condition that is to write the anomaly cancellation equation in terms internally of omega, of the function, and the licity condition is just a condition about the metric, because you want that the metric that omega u, that I considered before, of course, is positive. And mu is just a Choo-Choo form with integral 0 over the K-free surface. Okay, I will just mention that the solution of the Hull-Strominger system can be viewed as a relation with a geometric flow, what is called the anomaly flow, introduced by Fong, Picard, and Zhang. You see, you have a couple flow. You have essentially, and you ask that essentially the solution corresponds exactly to the stationary point of the flow. You see, you flow the metric omega, and you flow also the metric h on the holomorphic bundle. And the nice thing here that if you start with conformally balanced, the metric solution of your flow, omega t, is still conformally balanced. In the compact case, they show short-time existence and unicity. And the nice thing that for t going to infinity, the limit solve the Hull-Strominger. So they found a way using the flow to find, again, the solution by Fu and Yao with a different approach. Okay. Let's go to our theorem. And then let's see which example we found, new example we found. So we did a similar thing. We start with a compact K-free orbifold. So again, holomorphically, the canonical bundle is holomorphic trivial, Keller-Ricci flat. And we show ES is just the orbifold, Euler number. We take a pair or anti-cell dual one form, such that again, here we have the orbifold cohomology, integer coefficient. The Chern-Weil theory extends in this case. This is not a problem. So if we have a stable vector bundle of degree 0, such that satisfy this equation, this is exactly the previous equation writing by Fu and Yao in the specific way, then just by pullback. So you pull back W, you pull back the metric, you solve the Hull-Strominger system. So of course we have two difficulties here. First, okay, which type of K-free orbifold or orbisurface you can construct? The torus bundle, first thing, and then the more difficult thing a posteriori was to construct the stable holomorphic bundle. That was a bit less trivial than what we were thinking at the beginning. Okay, I quickly say something about the proof. The proof is essentially, okay, the first part you see, this part is essentially the same like Fu Yao, so no change. It's the same thing because you take the connection, one form, and then you have the condition that ensures that it's balanced, okay? And that's exactly, if you want to see topologically, is the condition that if you take the cup product of the two classes of omega 1 and omega 2 with the class omega s, so the Keller-Ricci flow, this is 0. So this is the same thing. We have holomorphic 2-0 form on S with cosine norm. Then automatically just taking the, this is not good. Just taking the wedge with theta, we get a holomorphic free 0 form with cosine norm with respect to our metric. And then we apply exactly like before the Fu Yao ansatz, so we get something conformally balanced. So here, is more or less the same. It's not changing much. That's the main remark. So we have a torus, in the case of Fu Yao, we have a torus fibration over a K-free surface. But then, if you look the proof and all the stuff, what you use is in fact that you have a foliation, a transversal Calabi-Yau foliation. So let's say you have a Riemannian foliation and the transverse holonomy is contained in SO3, in this case. How the foliation is generated by what? You just take the dual metric of theta and you take the real part and the imaginary part of such dual metric of theta, and you have this basic form. So omega b and small and omega big B are exactly the basic form that give the structure, and that's what we use. So we use it, that in fact you have a transfer Calabi-Yau structure. And then, of course, the difference from the previous case, that you don't have any more an analytic operator, but you have what is called a transversal analytic operator, because you have is only analytic in the part which is orthogonal to the orbit with respect to the action. And then we use some result by Kachimi that hold from transversal analytic equation. Now is analytic stuff like previous one. So the main idea is to use this fact that depends only on this foliated situation that we have. Okay, and let's see how we construct. I have still some minutes, right? How many minutes? 4 minutes, okay, good. So how we construct this bundle? Okay, this is something that cipher-S1 bundle appear are quite useful for the construction of Sasaki-Einstein structure, let's say, metric. Anyway, we start with S, our orbiform, so you have a singularity. In fact, the singularity that we consider are only isolated cyclic singularity. So we choose, we'll see in a moment, a specific orbifold surface in the Yano-Fletcher list, but in fact, this is what our student is doing. You can work with other type of such K-free surface, and we'll see what we get. Anyway, we start with S, and then we take the cipher-S1 bundle. Roughly speaking, you can think that outside union of Y divisor, you have a usual S1 bundle. Roughly speaking, I put more later, but I don't think that I have time to say more anyway. And then the important thing by color theory, we know when this cipher-S1 bundle is moved. Okay, and then we just take a smooth, let's say, a regular principal S1 bundle. So for that construction, when you don't have a product time S1, but you want something simply connected, you need a pair or rational divisor. Essentially, we satisfy some condition that ensure that the first cipher-S1 bundle is smooth, and then you have the second one that give you the second S1 bundle, principal bundle. Okay, the natural setting here, so essentially when you have a cipher as what is called cipher fiber manifold, you have a map to a complex and manifold such that every fiber is circle, roughly speaking. Here is really roughly speaking. But the natural setting is when X is a complex locally cyclic orbifold. So what we use is in fact the case when X is only isolated singularity of type E1. So the G in that case is zeta 2, the simple case. And okay, that's the way our color used to construct a cipher S1 bundle. Essentially everything is determined, but what is called the first chain class. But maybe I go, okay, I go to see which type of surface we consider. We consider an intersection in generic position of 2°6 hypersurfaces in that weighted Fourier space, P2, 3. And then using partial, essentially we use partial blow-up, partial resolution to construct the divisor that we need. And since we have a semi-free S1 action, and we can understand, and the dimension 6, the cohomologies understand, there are results that we can apply by Barden and also Collard. We can identify topologically, diffeomorphically, the type of manifold that we obtain. Here I skip this one. Okay. Essentially what we have is that we have that we get, you see, the first family involving connective sum of S2 times S3. K is related to the blow-up, let's say, the blow-up that you do in your construction. But K is going from 13 to 22. That's related to the B2, of course, is involved with that. And then, okay, the first, you have a factor as 1. But the second family, you see, is something which is simply connected. What we know now, maybe, is true, because one can ask, okay, you start from K equal to 13 and R equal to 14, and what about the previous number? Using other type of K-free or before, is possible to fill out all the number before. So with the same tricky, is still a work in progress of the student, or the PhD student, but is possible. And for K equal to 22 and R to 22 is exactly the Fouillard solution. I want just to mention this thing very quickly, that's I end, because I am late, sorry. I promised that I would. And that's essentially, I don't want to be technical here, but here for the construction of the stable, holomorphic stable bundle, we had to use essentially cell construction. Because you see from the previous equation, you need given a type of C2, right, to find out the right stable bundle with C1 0, because we want degree 0, but also we need some relation related to C and K, because we want the alpha prime has to be positive. That's the idea. Using cell construction, we were able to find out the I finish here. Sorry, I was 2 minutes maybe late. I finish here. Thank you very much for the attention. I hope that. Yes. Another correction. No. Okay. Okay. Granchalov and the brother Hempun study also way for which you can on the torus bundle over an Hermitian manifold. They found a condition for which you have valence. So in principle it's possible, but what is I think is not possible, at least I don't know, maybe other people know, is to find out a way to construct holomorphic bundle, because you also need holomorphic bundle then, and that is more difficult. That's why it's easier if you use scalar Ricci flat, like yeah. But that's a nice question, it's an interesting question. That's something that we would like to see, because maybe you can find something really maybe topological more different, right? And that is also related to the question that I mentioned at the beginning, to have a balance and pluriclose. Because with torus bundle over something that is non-Kähler, you can get both. So maybe there is some hope to construct something more general, because all the construction there are always using the base to be Kähler at least, or Kähler Ricci flat. That's, yeah. Yes, exactly. You can, in principle, you can, but I don't know what you get. With another student, we are looking at the case of projectivized bundle, but then the base is different. It's not, is in fact not the Kähler Ricci flat, but is an off surface, which is quite rich from geometric point of view for other things, but this is more related to the pluriclose case. We don't know if, probably balance case again, you cannot get, probably, I don't know. Yeah, that's, yeah, this bundle, in fact, many examples that come out are bundle, are torus bundle, let's say, but would be nice to have something with different fiber, yes. Yeah. You mean solution of the Hull-Strominger? Oh, yeah. As far as I know, there is no one constructing such solution for all the cases. So that's open, and that would be nice, of course. No, is because if you try with Stefan Ivanov, that's the guy that at some point say, okay, you need to have also this, but then in fact he didn't find an explicit. So that's another open question and nice, because from physics point of view you need because this is this is a mathematical develop because it's related to carnival transition, whatever, but would be nice to have, that's maybe other connection, not maybe not even unitary connection, just like metric connection. You have this plus and minus, right? This bismuth connection where the torsion, you just change the sign of the torsion. So maybe that's one possible way to get something. Yes, but there is not, is the connection that they use is still the chain connection, so it's not an instanton in that sense. I would say it is expected. Oh yeah, that's true. Yeah, that's true. Yes, maybe by T-duality. That's why Mario Fernandez is looking so much. And now we found also a nice picture in terms of current algebroid also about that. So maybe that's yes. No, I am. Sorry. So your system is really powerful. No, I didn't know. Sorry. I know, of course, the name, but never met by person. Yes. Points that physicists complain about this system. So there's one which is the sign of alpha prime, the other is the choice of the connection. Okay. Strictly speaking, there is another which is that alpha prime should be small. If it is then so those two corrections with curvature are decorated by extra corrections. I see. I didn't know about the control. I see. So very small. I didn't know who is the reference. Who is the reference of that for alpha prime small? Okay. He's known. This I didn't know, so I learned something more. Very good. Yeah. I see. Yeah, but my contribution is very small on that, so it's just a small understand. Yeah, that's good. Thank you.